Ladies and gentlemen, today is February 5th, year 2021. I am Pavel Mednis. I will read you the short lecture again on Fermat's problem to explain some questions stated by readers since the first lecture took place on January 8, year 2021. Algebraic proof of Fermat's last problem. Introduction. In 1995, in his paper, Andrew Wiles gave us the proof of widely known Fermat's last theorem. To remember, this theorem states that the power equation, formula 1, z powered n equal to x power n plus y powered n, where number n more than or equal 3 is an integer parameters, cannot have a solution for positive integer numbers x, y, z, except for the case they are equal to 0. So the problem has been solved since nearly 350 years have passed. Wiles' method of the proof is accessible for understanding only for professional mathematicians. However, his paper gives us the hope that Fermat's problem may be solved by means of a less complicated method intelligible for a wide group of people. In this paper, the algebraic proof of Fermat's last problem is given. Our proof is based on the known properties of integer solution of the degree equation and a simple logic. Proof. It is known, for instance, from the book of Kursh, that integer roots of the algebraic equation for unknown z of degree n with integer coefficients a sub n, where s is equal 0, 1, 2, so on, n. Formula 2, a sub n, z powered n plus so on, for the case of value n sub n equal 1, are located among integer divisors of free term a sub 0. Sometimes this statement is called Ruffin-Abel's theorem. The equation 1 is a special case only of the equation 2. Formula 3. Z powered n plus a sub 0 equal to 0, where free term is defined by the equality a sub 0 is equal to minus parenthesis x powered n plus y powered n for any integer x, y, n given. Explicit form of all integer divisors of equation 4 naturally is not possible to find. However, they exist really. For that reason we write a sub 0 is equal to p sub k L sub k formula 5, where p sub k are the integer divisors of the a sub 0, and respectively L sub k are quotients numbers received as a result of this dividing. Note the symmetry of 5 relative to permutation of values p sub k and L sub k. What is the consequence of the connection between them? Because of z is more than 0, the divisors of free term a sub 0, p sub k more than 0, we regulate so that numbers k equal to 1 to so on m and values p sub k are rising from minimal p sub 1 equal to 1, then k is equal to 1, to maximum meaning p sub m for any k equal to m, which we note as p sub m equal to minus a sub 0. Then the meaning of quotients are expressed by virtue of dividers found from formula 6. L sub k is equal to minus p sub m plus 1 minus k less than 0. Let me test formula 3 by means of substituting of z equal to p sub k in account with relations 5 and 6. As a result, we derive m relations connecting all divisors. Formula 7, p sub k powered n minus 1 equal to p sub m plus 1 minus k. Are they fulfilled? Let m be an even number. The lower strings of this presumed equation, starting from the number k equal to m over 2 plus 1 up to the number k is equal to m, are not realized because of numbers of divisors on the left side are bigger than the corresponding number of divisors on the right side. The first string of the upper part of equation 7 is not realized also because of the left side is equal to p sub 1 equal to 1, but the right side is equal to p sub m more than 1. In the group in the group of remaining upper strings of 7, it is not possible to be the sign of equality in any two or more strings at the same time. Indeed, Let us consider sufficiently case for any two strings with numbers k sub 2 more than k sub 1. Then from 7 we get equation 8, p sub m plus 1 minus k sub 2 more than p sub m plus 1 minus k sub 1. However, this inequality is in contradiction with our regulation of dividers. So, in the upper part of 7 remain only one string with the sign of equality. It is the string with number from series of numbers k equal to 2, so on, m over 2. Is this string fulfilled from 7? We shall get the answer below. To be continued. Let now m be odd. For odd m, the string in 7 with k equal to half of number m plus 1 have no pair. The equation for divisors pair sub k with such a number is presented by the formula 9. P sub k powered n minus 1 equal to p sub k. For meaning n equal to, this equation transforms to equality with undefined value of p sub k. Therefore, this divisor permits us to find the known roots of formula 3 in integer numbers. For the case n more than or equal 3 from the equation 9 follows that these divisors are equal, p sub k equal to 1. But any such divisors, it is obvious, are not the root of the 3. Also, the string with the other numbers for n equal to do not lead to the sign of equality in 7. In other strings, for the case n equal or more than 3 are forming m minus 1 equation like 7 considered above. For the case of even m, the result is similar to what was discussed earlier. In the string with numbers which are larger than half of number m plus 1, the sign of equality are impossible. In the group of upper strings 7, from all strings it is possible the sign of equality in one string only. It is any string with number k equal to, so on, m minus 1 over 2. For case of odd m. So we get here the same question such as in the case of even m. In this string fulfilled from 7. Any of the strings selected from the upper part of 7 is by form of the type 3. Indeed, she may be considered as any algebraic equation for unknown p sub k of degree n minus 1 with free term equal to minus p sub m plus 1 minus k. After applying the method of analysis of such equation used above, we can write like 7 the new equation presented by formula 10. P sub k, k sub 1 powered n minus 2 equal to p sub k m sub 1 plus 1 minus k sub 1. Here, p sub k, k sub 1 are the positive divisors of number minus p sub m plus 1 minus k for the k given, and which are regulated as before. Let be m sub 1 the amount of these divisors. In this equation, index k sub 1 equal 2, so on, m over 2 for even m sub 1. For the case of odd m sub 1, we have k equal to 2, so on, m sub 1 minus 1 over 2. We see that for value n equal 3, in 10, the left side is less than the right side. Hence, equation 7 is not valid for n equal 3. We can proceed construct this once more to get the next equation presented by formula 11. P sub k, k sub 1, k sub 2 powered n minus 3 equal to p sub k, k sub 1, m sub 2 plus 1 minus k sub 2 with a new positive divisor p sub k, k sub 1, k sub 2 of number minus p sub k, m sub 1 plus 1 minus k sub 1 for the k and k sub 1 given in 10. Let be the total number of these dividers are m sub 2. Then permitted index k sub 2 equal to 2, so on, n sub 2 over 2 for even m sub 1 sub 2, and k equal to 2, so on, m sub 1 minus 1 over 2 for odd m sub 2. We see that for value n equal to 4, in equation 11, the left side is less than the right side. Hence, equation 7 is not valid for the case n equal to 4 also. We can proceed this procedure once and again until they lose their sense. So, after a number of steps q more than 1, we can get the equation 12. P sub k, k sub 1, so on, k sub q powered n minus 1 minus q equal to P sub k, k sub 1, so on, k sub q minus 1, n sub q plus 1 minus k sub q. The sense of all notations used in this formula is similar to 10 and 11. The right side of 7, 10, 11 and 12 are always greater than the left side. If we choose the value of power on the left side b to be 1. So, in any string of 7, it is not possible the sign of equality. This means that under condition n equal or more than 3, there are not at all any solution of 3 with integer number. What we have to prove? Conclusion. The main idea of the proof suggested above is concluded in compose the system of equation for the unknown integer divisors of a sub 0 and formula 5 and 6. The method used permits us solve also the widely known, the generalized form of Fermat's problem, and to consider also the rational proof of equation 2 when the integer coefficients a sub 1 is not equal 1. About this problem I shall tell you in my following lecture. However, I should see these results early whenever my text lecture takes place. References: Wiles, Courage. Date: February 5th, year 2021. Thank you.